Good day to you all. Here, We Learners Note is an online solution to encourage a better way of education to all of our students. Here, I am Sarika V.S., your physics teacher. Let's start our topic, that is Bernoulli's theorem and its applications. Okay, let's start with our Bernoulli's theorem. Here, we will discuss about the statement of Bernoulli's theorem and its equations and its applications. Let's start. It's our Bernoulli's theorem. According to Bernoulli's theorem, the sum of kinetic energy, potential energy and pressure energy of a unit mass of liquid will be constant. And one of the important thing is that the fluid should be non-viscous and it should be incompressible. And also the fluid should be in a streamline flow. Okay, before going to the details, we have to familiar with the some terms relating with this Bernoulli's theorem. That is the term pressure energy. What do you mean by pressure energy? Pressure energy is the energy due to the variation of pressure between 2 points of a liquid. If there is a difference of pressure between 2 points of a liquid, there will be an energy exist in that particular area. Okay, that is known as pressure energy. Okay, if the fluid is in a stationary condition, the pressure energy, the only energy existing is the pressure energy. If the fluid is in moving condition, that fluid will contain pressure energy and kinetic energy. The next term is about kinetic energy. What do you mean by kinetic energy? Kinetic energy is the energy due to the motion of a body. If the fluid is in a motion, that is if the fluid is flowing, it will be having a velocity. Due to that velocity, that fluid will be having a kinetic energy. The next term is pressure energy. Next is potential energy. Potential energy is the energy possessed by an object by virtue of its position and its alignment. In the case of fluids, if the fluid is situating at a particular height from the ground level, that fluid will be it will be having a potential energy and its value will be equal to mgh. Depending upon the height, the potential energy will be different. Higher the height, higher will be the potential energy. Okay, then next, the term streamline flow. Streamline flow is the condition in which all the layers means if we have a fluid, each of the fluid parts will be flows in the form of a layer. Okay, so each of the layer of a fluid will be flow in a uniform condition. That is known as the streamline flow. If the velocity of each of the layers are not equal, it will be in a turbulent condition. That is represented like here. This is the streamline flow condition and this is the turbulent flow condition. Here we can see that each layers of that liquid are in uniform motion condition. Here in the case of turbulent flow, each of the layers of that liquid are in random movement condition. That is known as the turbulent flow. Okay. Then next we are going to derive the equation, that is we are going to find the expression for this Bernoulli's theorem. For that we have to familiar with this picture. Okay, this picture represents a pipe having different areas. Here you can see that the A1 is the area of this portion and A2 is the area of this portion. It have different areas. Okay, and here V1 is the velocity of liquid in this A1 area and V2 is the velocity of the same liquid at the A2 area. And delta x1 and delta x2 is the amount or distance that fluid moved in unit time. Okay, so at unit time, each part of the fluid will be flow a distance of delta x1. Okay, then we have to familiar with the other term, that is continuity equation. What is continuity equation? Continuity equation is shown here. What it means? A1 V1 is equal to A2 V2. Here A1 is the area and V1 is the velocity at the first point. Then A2 is the area and V2 is the velocity at the second point of that pipe. Okay, this A1 V1 and A2 V2 will represent the quantity, that is mass of liquid flows from portion 1 to portion 2 in unit time. The time can be in 1 second or 1 minute, etc. Okay, so this is a continuity equation. That is, what it means is that the quantity of the liquid flowing out from a particular region in unit time will be equal to the quantity of the liquid going out from a particular area in unit time. Okay, so this is A1 V1 is equal to A2 V2 is our continuity equation. We have to apply this equation for the derivation of Bernoulli's principle. Okay, so this is our equation. Here we are starting our derivation. For that we are applying our continuity equation, that is A1 V1 is equal to A2 V2, which is equal to V. Here this capital V indicates the volume of the liquid displaced from that particular point, initial point, that is here this is the area 1 region and this is the area 2 region. Okay, so A1 V1 will give the volume of liquid displaced from this portion in unit time, and A2 V2 indicates the volume of liquid emerging out from that portion at unit time. Okay, so here is our continuity equation. Then next we are going to discuss about the pressure energy. Pressure energy is the energy due to the variation of pressure in these two regions of the pipe. Okay, here P1 A1 indicates the force experienced to the fluid in the region, first region. Okay, and P2 A2 indicates the force experienced by the fluid on the second region. And if we are multiplying this P1 A1 with V1, it will give the pressure energy. It is the representation of pressure energy. How? Because P1 A1 is equal to the force into displacement will give the energy. How this V1 term comes as an displacement? Because V1, here this V1 represents the velocity per unit time, that is V1 divided by time is equal to 1 unit. Okay, so that V1 divided by 1 will give the distance. That distance is known as the displacement. Okay, so here we got the representation of P1 A1 into V1 will give you the total energy or work done. Okay, like that P2 A2 into V2 will give the total work done by the pressure at the region 2. Okay, then we can see that we have a relationship A1 V1 here, and here we have A2 V2. Then according to our continuity equation, we can replace this A1 V1 by volume V and A2 V2 by volume V, because both these volumes are same. Okay, so these equations become P1 V and P2 V. These two equations are represented as 2 and 3. Next is about the difference of work done between the first and second points of the tube. In the first point, that is at the initial point of that tube, the work done, that is the potential and kinetic energy, is provided from this variation of this pressure energy. Okay, so for that we have to find the difference of pressure energies. We have to find the difference of pressure energies between the first and second point of the tube. Okay, so this is the difference of potential energies between the first and second points of the tube. That is P1V minus P2V. This P1V minus P2V will be a value greater than 0. Why? Because this P1V is a higher value than that of the P2V. Okay, this pressure difference and this variation of or this difference of pressure energy causes to the movement of fluid from first level to the second level. That means the velocity of that fluid is changing. If the velocity of a fluid is changing, what will be happen? Its kinetic energy will be changes. Okay, so change of kinetic energy of that particular fluid is represented by increase of kinetic energy is equal to half mv2 square minus half mv1 square. That is half mv2 square is the second velocity, that is increased potential energy corresponding to the increased velocity. Half mv1 square is the kinetic energy relating to the initial velocity of that fluid. Then correspondingly there will be an increase of potential energy. How? Increase of potential energy will be happen only if the height is increased. Here we can see that in this picture, the portion 1, the first portion is at this level, okay, and the second portion is at this level. So with respect to the ground level, the height of the second portion is higher than that of the first portion. So if a fluid is flowing from this region to the second region, surely the height, the h will be increases. Correspondingly, there will be an increase of potential energy. The increase of potential energy is represented by mgh2 minus mgh1. Okay, then we can see that this P1 minus P1V minus P2V is equal to mgh2 minus mgh1 plus half mv2 square minus half mv1 square. That is, the difference of this pressure energy causes to the moment of fluid. Okay, so that difference of pressure energy, the difference of pressure energy causes to the increase of kinetic energy and potential energy. So we can equate these two equations. So P1V minus P2V is equal to mgh2 minus mgh1 plus difference, that is increase of kinetic energy, is half mv2 square minus half mv1 square. Okay, then we can make some rearrangement to get a better representation of this Bernoulli's equation. Okay, for that we are getting rearranging this equation, that is for getting a better solution. We can see that this P1V minus P2V is equal to mgh2 minus mgh1, and here half mv2 square minus half mv1 square. Then expanding, that is by opening these brackets, the same equation will be like this, the second line. Okay, then rearrange this equation, that is here this is an equation A, then rearranging this equation, that is rearranging all the 1 terms on one side and all the 2 terms on the second side. Okay, so P1V, you can see that P1V plus mgh1 plus half mv1 square, all of them will become on the left side, and P2V plus mgh2 and half mv2 square on the right side. Okay, then you can see that divide each of the term of this equation on the left and right side by m, that is m is the mass. Okay, so the equation will become like this, divide each of the term by m. Okay, it will be appear on all the terms. Okay, then cancel any of the common terms are came here, you have to cancel. So cancelling this m and this one, here these m's are cancelled, here also, here. So this will be the last final representation, not the final, it will be the representation after cancelling this mass values. This will be the last representation after cancelling all m values. So P1V divided by m plus gh1 plus half v1 square is equal to P2V by m plus gh2 plus half v2 square. Next, we have substituted the value of rho in the place of m by v. That is, the equation become, this equation become P1 divided by rho plus gh1 plus half v1 square is equal to, here this m by v is also changed by rho, it is replaced by this rho. Okay, so P2 by rho plus gh2 plus half v2 square. Then again we are making some rearrangement for getting a better representation. For that we are making, that is, here we have 1 is equal to 2 is equal to 3, like that. Here we can get a relationship like this. Okay, it is a continuity relationship. So we can replace this representation as a single one like this, that is P divided by rho is equal to gh plus half v2 square is equal to constant, because the value on the left side will be equal to the value on the right side. So that's why we are representing this equation, this 9th equation, by using a common equation like this. Okay, so this P1 divided by rho plus gh1 plus half v1 square, its value will be equal to that of the on the right side. So the equation becomes like this. Then again we are making some rearrangement, that is we are changing this rho term here. We are replacing this rho, that is by finding LCM values we can replace this rho from here. So our equation will become like this. Okay, so our final equation relating to our Bernoulli's theorem is equal to half rho v square plus rho gh plus p is equal to a constant. Here this p relating to the pressure energy term, this rho gh represents to the potential energy term, and half rho v square is relating with the kinetic energy term. That's all. So this is our final representation of our Bernoulli's theorem. Here each of the term you are familiar with these terms, that is rho is our density and h is our height and v is the velocity, p is our pressure. That's all. Next, we can conclude from this, conclude means according to this statement we can see that the total energy of a fluid is conserved. That means in this equation half rho v square plus rho gh plus p is equal to constant. That is the total energy relating to a fluid is constant. It will not change at any cost. That is the concept of Bernoulli's theorem. And so this equation and this statement can be utilized for finding some physical values in our daily life. That is the application. The first one is for finding the pressure and velocity of a fluid. Bernoulli's theorem can be used for finding the pressure and velocity of fluid. Okay, again it can be used in the Venturimeter. Venturimeter is used for measuring the rate of flow, that is flow rate, the speed with which a fluid is flowing. Then next one, it is used for finding the shape of a aeroplane wings. The shape of an aeroplane wings is depends upon the pressure difference between the upper and lower levels of that wing. So this Bernoulli's theorem helps to find the pressure difference between the upper and lower level of the wings. Okay, then we can use Bernoulli's theorem for finding the answer for this question. That is, while a train comes, we tend to fall towards the train. Why? Why this is happening? This can be explained with the help of Bernoulli's theorem. That is, according to Bernoulli's theorem, if there is a change of pressure difference, there will be force acting on that body. Okay, like that we can see that if a train passes, okay, there will be a pressure difference between our body and the train. Okay, the pressure between our body and the train will be changes. Okay, so there is a pressure decrease. This pressure decrease causes to the pulling effect of our body from backside. Bernoulli's theorem can also be used for finding the solution to this question. That is, while a train comes, we tend to fall towards the train. Why? The answer is here. The answer is here. We can apply Bernoulli's theorem to find the answer. That is, if a train passes very fastly, the air between our body and that train will moves very fastly. That is, the velocity of air in between our body and the train will become very fast. So what will be happen? According to Bernoulli's theorem, if the velocity increases, what will be happen is pressure. Its pressure will get reduced. So if the pressure between our body and the train is decreased, the air behind from that person will be pushes that person towards the train. Why? Because the pressure of air behind that person will be higher. So what will be happen? The air from higher pressure area will be flows to the area where the pressure is low. So what will be happen? That person will be fall towards the train. Let's conclude our topic, that is our Bernoulli's theorem and applications. Then according to Bernoulli's theorem, we can see that the total energy of a fluid is conserved. That is, the sum of kinetic, potential and pressure energy of a particular quantity of fluid is conserved. And we have a lot of applications to this Bernoulli's theorem in our daily life. Dear students, hope all of you understood the topic we have discussed on today. We have a lot of videos relating to our subject on our official website www.learnersnot.com. Here I am Sarika VS signing off.